Welcome back. We are continuing answering this. Make sense of every question in this question paper. I hope you are still together and enjoying the session. Very good question. Again, in question number 5, they say the reaction between aluminium and excess sulfuric acid is used to investigate factors affecting the rates of reactions. The question is given there. Investigation number 1, if the effect of a catalyst on the rate of reaction is determined. Think aluminium powder of mass 5 grams reacts with excess 0.1 mole per dm cube of sulfuric acid at 60 degrees. Consider the following energy diagrams not drawn to scale for this investigation. X and Y in diagram B represent the activation energies. Yes. On this one, you can see that the reaction obviously is exothermic because the energy of the reactants is higher than that of the products. Fine. Remember, in this case, now when you analyze this, you'll find that now the shaded area obviously represent the particles with enough kinetic energy. Fine. Now let's see the questions. 5.1.1. They say, is the reaction between aluminium and dilute sulfuric acid exothermic or endothermic? According to this, they say they give reason for the answer by referring to the above diagrams. So look at this diagram. Obviously, the one that is telling us that the reaction between aluminium and dilute sulfuric acid should be an exothermic. 5.1.1. Therefore, our answer will be exothermic. And then we have already talked about that one. The reason is that energy, the potential energy of reactants is higher or greater than that of products. I think in this case they will accept as well if you can say energy is released. And then as well if you can just say delta H is less than 0. And last option will be when you do calculation and say delta H is negative 121.7 kilojoules. I think this will also be accepted because now the learner is becoming mathematical. So the difference in this case between these two is that 121.7. Very interesting question. Now let's move and then talk about the next question. 5.1.2. they are asking us to say, with the knowledge that we have gained now, have a look at this one. Look, we are fine. What does the shaded area to the right of line P represent? As we said, in this case, in the Maxwell-Boltzmann curve, therefore the shaded area represent the particles with enough kinetic energy. There are many where I think we will have to accept also if a learner can say these are particles with kinetic energy that is greater or equals to the activation energy. That is greater than the activation energy. So it's fine. Greater or equals to, I think is also fine. Yes, greater or equals to the activation. That is enough, because enough is always relative. Our benchmark here is activation energy. Fine. 5.1.3, they are saying to us, determine the numerical value represented by the letter X on diagram B. X represents the activation energy without catalyst. We look at this one to say, upon this one, the activation energy without catalyst is when we move from 208.2 to 240.8. Therefore, in that case, the answer will be 32.6 kilojoules. 5.1.4 or 5.2.1. 5.2.1. Now we move to the next question, which is 5.2.1. Yes, we are still on this. Investigation is number 2 now. They're telling us to say in investigation 2, the investigation is now repeated at 30 degrees. We are decreasing the temperature now using the same reactants, 5 grams of aluminum and excess 0.1 mole per dm cube of sulfuric acid and a catalyst is maintained. How will this affect each of the following when compared to the investigation in 1? In other words, when you decrease the temperature, what happens to the following, right? Increase, decrease. Choose from increase, decrease, or remains the same. Now 5.2.1, what will happen to the size of the shaded area? Obviously, when we decrease the temperature, that size will decrease, because anyway we are decreasing the temperature. 5.2.2, what will happen to the value of Y? The value of Y, this is the activation energy with catalyst. If you increase the temperature, if you decrease the temperature, what happens to the value? This is the activation energy with catalyst. So that will remain the same, obviously. That remains the same. Remains the same. And then 5.2.3, what will happen to the total volume of hydrogen gas produced? Whether we use decreased temperature, that one affects the rate, it doesn't affect the yield. Therefore, it means that now the yield of the product remains the same. It remains the same. So decrease or change in temperature affects the rate, doesn't affect the yield. Now we move to investigation number 3, 5.3.1. It will be the next question. They're telling us to say in investigation 3, in this investigation, 5 grams of the same sample of impure aluminum powder reacts with an excess diluted sulfuric acid at 60 degrees. Temperature remains the same in each of the 3 runs. The table below summarizes the conditions and the results obtained. Assume that the impurities do not react. Now we are given the table. You can see in the table that from run 1 up to run 3, the concentration of sulfuric acid was changed, and then that affected the average rate of producing hydrogen in this case. Now they are telling us to say, write down the independent variable for this investigation. What is changed? Obviously, from run 1 to run 3, concentration was changed. It's concentration. If you want to be explicit, you will say of sulfuric acid. The concentration of sulfuric acid that was changed. And then 5.3.2, use collision theory to explain how the average rate of the reaction is affected in this investigation. You know how to deal with concentration. You say increase in concentration from run 1 to run 3. Concentration increases, or implies that more, increases the number of particles per unit volume, or increase in concentration implies that more particles per unit volume. That will be short. And then once more particles per unit volume, that more particles collide with, remember, with concentrations about the number of particles colliding with correct orientation. And then once more particles collide with correct orientation, means that more effective collisions now. Effective collisions per unit time. Remember, that is very important. You cannot rule. If you can just say more effective collisions, you will be wrong because the rate is not mentioned there. Fine. Now we come to 5.3.3. The last question, calculations. Now find 6 marks are up for grabs. The time for the reaction to reach completion in run 3 is 2.6 minutes. Calculate the percentage purity of aluminium. Take the molar gas volume at 60 degrees to be 27,000 cubic centimeter per mole. No problem. We start from average rate because it's in run 3 is 40. Then we say, okay, fine, let's calculate the final volume of hydrogen. Then the average rate equals to delta V over delta T. We are guided by the units here. Please be careful. Guided by these units. If it's cubic centimeter per second, therefore we're going to use delta V over delta T. The average rate is 40 is given, and then the final volume minus the initial obviously is 0, and then divide by 2.6 multiplied by 60 because it's per second, this average rate. And for the final volume, it will be now 6240 cubic centimeter. That is the volume that will produce at the end in this experiment. Fine, we move on. We've got the final volume. Now we can calculate the number of moles of hydrogen with that volume. Yes, number of mole of hydrogen with that volume, then it will be volume over Vm, which is the same as 6240 divided by 27,000 is given. Therefore the answer gives us 0.231 mole. That is the number of mole that will be produced in this case if that volume of 6,240 is produced at the end for hydrogen. Yes. Now once we know the number of moles, we can now determine the number of mole of aluminium using that of hydrogen. Yes, because they are in a balance equation. According to this one, then it will be now 2 over 3 multiplied by 0.231, which will give us 0.154. If you don't understand this one, no problem. We say according to the balance equation, in this case, you find that now number of mole of aluminium is to number of mole of hydrogen. They are in the ratio 2:3. I don't have 3, I've got 0.231 is to x. You cross multiply, you will find that x equals to 2 times 0.231 divided by 3. That's where now we get that. So hope you understand now. Thank you. And then after finding the moles, now we come to the mass of aluminium. Mass of aluminium that is produced by those moles. Number of mole will be now 0.154 multiplied by aluminium is 27. Therefore the answer you get 4.16 grams. Now they are saying calculate the percentage purity in that sample. Therefore percentage purity in this case, this mass of 4.16 is in the 5 gram. Then 4.16 divided by 5 multiplied by 100%. Then our percentage purity becomes 83.2%. That is our final answer in this question number 5, the last one. Can you see we got the 6 marks? Well, now they were saying calculate the percentage purity of aluminium take the molar gas volume as at 60 degrees as 27,000 cubic centimeter in this case. So that's how we reach the end. So our final answer will be 83.2. So I hope you are following, which is very good stoichiometric calculation where we relate moles in a balance equation. Until we meet in the next session of chemical equilibrium, thank you.